Hi! In the previous lectures, we covered the main principle of mutation testing and introduced some common mutation operators. With these building blocks, we can finally see how to use mutants testing in practice. There are three main steps in mutation analysis. The first step is generating mutants using the mutation operators. Then, the test code is executed against each mutant using an execution engine. In the final stage, we have to analyze the test results. Upon test execution, the mutants are classified in two categories. A mutant is killed if the test suite fails when executed against the mutant while it passes on the original program. Instead, a mutant is alive when the test suite passes on both the mutants and the original program. An adequate test suite should kill as many mutants as possible. However, as you will see later in this lecture, killing mutants is not always possible. Based on the ratio of killed and alive mutants, the quality of the test suite can be measured using the mutation score. The mutation score is defined as the ratio between the number of killed mutants onto the total number of mutants. Based on how developers use the mutation score, quality assurance activity can be divided in mutation analysis and mutation testing. These two terms are often used as synonyms. However, there is a subtle difference between them. Mutation analysis indicates the process of assessing the quality of the test suite by simply computing the mutation score. Instead, mutation testing denotes the process of improving the quality of the test suite using the mutants. Indeed, if some mutants survive, it means that likely we need to improve the test suite by adding new tests or changing the existing ones. As I mentioned before, not necessarily alive mutants imply a non-adequate test suite. It is indeed possible that some mutants cannot be killed at all, whatever test case we use. This is the case of equivalent mutants. A mutant is said to be equivalent if it always behaves as the original program. Here, the definition of equivalence is related to the definition of program equivalence. Remember, two programs E and B are functionally equivalent if they always produce the same output on every input. In our context, whatever test case we write, the equivalent mutants will always return the same output of the original program. Let us consider the following Java code. The method contains a while loop, and in each loop, the variable index is decreased. When the value of the index is equal to 0, then the while loop ends. If we use the relational operator replacement, we will end up with the mutants where the lower or equal operator replaces the equal operator. These two programs are functionally equivalent. Whatever input value we consider, the while loop will always end when the index is equal to 0. This is an elementary example of equivalent mutants. Because of equivalent mutants, the equation for mutation score needs a critical fix. As denominator, we have to consider the total number of non-equivalent mutants rather than the total number of mutants. While trivial cases of equivalent mutants can be automatically discovered, it is impossible to detect all equivalent mutants in an automated fashion. This is because the problem of detecting equivalent mutants is a non-decidable problem, just like detecting invisible paths. Therefore, when you use mutation testing, you should always check the mutants that are alive because some of them might be unkillable. At this stage, you may ask yourself whether mutation testing is useful in practice. For example, we may question whether the test suite that kills more mutants can indeed detect more real faults. There are many research studies done in software engineering trying to shed some light on these aspects. All existing studies show that mutants could provide a good indication of fault detection ability of a test suite when the mutants operator are carefully selected and when equivalent mutants are removed. Another study by Just et al. Also showed that mutant detection is positively correlated with the real fault detection, and this independently of code coverage. This correlation is stronger than the correlation between statement coverage and real fault detection. This means that the mutation score is a stronger measure of the fault detection capability of the test code. The benefit of mutation analysis has a price to be paid. Indeed, it can be particularly expensive to run in the real world. To explain this, let's do some computation. Let's assume we have a code base with 300 Java classes and a test suite with 10 test cases for each class. Let's assume also that, on average, each test case requires 0.2 seconds for its execution. In total, the cost of executing the entire test suite is of about 10 minutes. Let's suppose that the mutation operators generate 20 mutants per each class on average. Since we need to run the test suite against each mutant separately, the cost of computing the mutation score is proportional to the total number of mutants. In our example, the overall cost is about 3 hours and 20 minutes compared to 10 minutes needed for traditional testing, meaning the time needed for running the test suite. Over the last decades, the researchers investigated multiple ways to reduce the cost of mutation analysis. A classical cost reduction technique consists in looking at reachability condition. More precisely, we know that a mutant cannot be killed if the test suite does not cover the statement where the syntactic change has been injected. In other words, coverage is a necessary condition for killing the mutants. We cannot kill a mutant if you don't cover it at least once. Based on this observation, we can define two simple cost reduction heuristics. The first one consists in running the test suite on the original program to identify first the covered lines. Then, mutation analysis is performed based on the coverage data. Mutants located in code lines not covered by the tests can be skipped. Another simple heuristic consists in stopping the execution of the test suite as soon as the mutant is killed. This means that once the mutant is killed, there is no need to run the remaining tests for it. More advanced cost reduction techniques rely on the following observation. Mutants generated by the same operators and injected in the same location, code instructions, are likely coupled with the same type of real faults. Therefore, we could select only a subset of the generated mutants rather than them all. This heuristic is often referred to as do fewer. The most straightforward do fewer heuristic is random sampling. However, other heuristics can be used, such as eSelective or clustering mutants and operators. Nowadays, there are many mutation testing tools publicly available for most of the programming languages. Here, we have just some tools for Java, JavaScript, PHP, and C. Therefore, this is not an exhaustive nor a complete list. One of the most mature tools for Java is PIT testing, which is a publicly available tool for Java code. PIT testing can be launched via command line, but is also integrated into most popular IDEs like Eclipse or IntelliJ, in Maven and in Gradle. PIT testing also provides the test execution report with the mutation score for each class. Besides, it also allows you to inspect the source code and the mutants. This concludes our lecture on mutation testing and analysis. Now it's time to have fun and to use mutation to assess your test suites.